Okay, now I would like to explain about the magnetic potential. The magnetic potential are divided into two types: scalar magnetic potential and vector magnetic potential. Okay, magnetic, scalar and vector potentials. In electrostatics, it is seen that there exists a scalar electric potential. In electric fields, we know that electric potential is there, so which is related to electric field intensity E bar equals to minus del V. Okay, similarly in magnetic fields, there are two types of potentials. First one, scalar magnetic potential, it is represented by Vm. The vector magnetic potential, it is represented by A bar. So first one, scalar magnetic potential, it having only magnitude. If Vm is the scalar magnetic potential, then there must satisfy the equation del bar cross del Vm equals to 0. So curl of gradient of any vector, any scalar equals to 0. So this is the property of the vectors. But the scalar magnetic field, magnetic potential is related to the magnetic field intensity h bar equals to minus del Vm. Okay, in electric fields we know that relation E bar equals to minus del V. In magnetic fields, similar parameters. In place of electric potential, in magnetic fields we are having scalar magnetic potential, it is represented by Vm. In electric field intensity, so similar parameter in magnetic fields is magnetic field intensity. So the relation between magnetic field intensity and magnetic potential, h bar equals to minus del Vm. So substitute this equation in this equation. So next equation, del bar cross minus h bar equals to 0. So we know that the Maxwell's third equation, curl h bar equals to 0. So let this equation number 1 and it is equation number 2. So from equations 1 and 2, j bar equals to 0. See equation 1, curl h bar equals to 0, equation 2, curl h bar equals to j bar. By comparing these two equations, we can write j bar equals to 0. So it means the scalar magnetic potential, so Vm is defined for source free region, so where j bar is absent. So that is current density equals to 0. So current density equals to 0 means current equals to 0. The scalar magnetic potential present, so when current density equals to 0. So the current density equals to 0 in case of permanent magnets. So it means the scalar magnetic potential exists only in permanent magnets. So in this case only, in permanent magnets case only, the magnetic field is present even though the current equals to 0. So h bar equals to formula minus del Vm only for j bar equals to 0. So similar to the relation between E bar and V, the magnetic scalar potential can be expressed in terms of h bar is, so Vm equals to minus integral b to a h bar dot dl bar. In electric fields, we know that relation V equals to minus integral b to a e bar dot dl bar. So similarly in magnetic fields, the scalar magnetic potential Vm equals to minus integral b to a h bar dot dl bar. So next one, Laplace equation for scalar magnetic potential. So we know that the Maxwell second equation. So closed line integral b bar dot ds bar equals to 0. So by applying divergence theorem, we can write it equals to the volume integral divergence of b bar equals to b bar into dv equals to 0. So divergence of b bar equals to 0. B bar equals to mu into h bar, substitute. So del bar dot mu into h bar equals to 0. Del bar dot h bar equals to 0. H bar equals to relation minus del into Vm. So del bar dot minus del into Vm equals to 0. Del square Vm equals to 0 for j equals to 0. So this is the Laplace equation. The above equation is called scalar magnetic potential Laplace equation. This is similar to Laplace equation for scalar electric potential del square V equals to 0. In electrostatics, the electric potential Laplace equation del square V equals to 0. So similarly in magnetostatics, del square Vm equals to 0, Laplace equation. Here Vm is scalar magnetic potential. Okay, next one. Okay, del bar cross B bar equals to mu naught into J bar. Okay, next one. Okay, this is vector magnetic potential. The vector magnetic potential is denoted as A bar. It is represented by A bar and measured in Webers per meter square. The scalar magnetic potential units are amperes. The vector magnetic potential units are Webers per meters. It has to satisfy the equation del bar dot del bar cross A bar equals to 0. Here A bar is vector magnetic potential. So del bar dot B bar equals to 0, Maxwell's second equation. By comparing these two equations, we can write B bar equals to del bar cross A bar. So the curl of a vector magnetic potential is the flux density. The curl of a vector magnetic potential equals to flux density. So next we know that the Maxwell's third equation del bar plus h bar equals to j bar, h bar equals to b bar by mu. So del bar cross b bar by mu equals to j bar. So next equation, del bar cross b bar equals to, if it is in free space, it equals to mu naught into j bar. So del bar cross a bar equals to mu naught into j bar. Okay, we know that b bar equals to del bar cross a bar. So by using vector identity, we can write del bar cross a bar equals to del into del bar dot a bar minus del square into a bar equals to mu naught into j bar. So j bar equals to 1 by mu naught. Del bar cross a bar, it equals to 1 by mu naught del into del bar dot a bar minus del square into a. So by using the above expression, if vector magnetic potential is known, we can find the current density. So this is the relation between the vector magnetic potential and current density. So next one, Poisson's equations for magnetic field. So from this equation we can write this equation here. So del square a bar equals to minus mu naught into j bar. So this value equals to 0. So divergence, the gradient of divergence of any vector equals to 0. So del square dot a bar equals to minus mu naught into j bar. The above equation is called Poisson's equation for magnetostatic fields. This is Poisson's equations for magnetostatic fields. Okay, next, characteristics of scalar magnetic potential. So first one, the negative gradient of Vm is given by h bar equals to minus del Vm. The scalar magnetic potential exists only when j bar equals to 0, and it satisfies the Laplace equation del square Vm equals to 0. The relation between scalar magnetic potential and magnetic field intensity is Vm equals to minus integral h bar dot dl bar, and the scalar magnetic potential units are amperes. So next, the characteristics of vector magnetic potential. It is represented by a bar. It exists only when j bar is present. So it means it is present if current not equals to 0. In case of electromagnets, the magnetic potential is called vector magnetic potential. The Poisson's equation is del square into a bar equals to minus mu naught into j bar. If j bar equals to 0, del square into a bar equals to 0, and divergence of curl of a vector equals to 0. So del bar cross a bar equals to 0.